Alrighty, guys, can you hear me again?
Yep.
So are there any questions about what we did in the first half? Anything you want me to talk about one more time?
Professor, could you go over the relation between the example problems that were how that related to the new change of measures that you lectured on earlier?
Yes. The thing that the calculation, so it's related, but it's not quite the same. I think it was a homework problem. It was this homework 5. The calculation we did in one of the Radical derivative processes was highly related to what you have here. And some of you guys, for your midterm, you went through this problem here with me. So the calculations that are behind problem number 1, and then that example with the heads and the tails, this is quite related to this calculation here.
Okay, I do recall that. Was there a relation to the change of measure with the few examples you did?
Yeah, I mean, so right, so what we will, so this will be next time, but we'll create new meshes. We'll create new meshes. So it's like Q. By specifying either, the one way that you can do it is you can specify say dq dp. So this is the radical derivative. We can either specify that, or what you can specify is the entire martingale, so the radical derivative process. Right, that's my Cn here. And this one here is simply C. This is the radical derivative process. It's a long thing to write, but let me write it out. All right, so you can either do, if you want to create new meshes, the way that we're going to do it is either specifying it, either by specifying the radical derivatives of dq dp, or by specifying this full martingale, the Zn. Like, so for example, if you have a 2-period binomial model, for example, if you do a 2-period binomial model, then I can specify the radical derivative, or I can specify Z2. A 2-period binomial model, then you'll have Z0 will be 1, you'll have a Z1, and you'll have a Z2. So for example, how do I get Z2? Right, my omega here, this is heads, heads, tails, tails, heads, tails, tails, head. So what I need to do is I need to specify what is P tilde on these 4, right? So what would be like P tilde on heads, heads. How would that work out? Well, I want to write this. I want to write this as an expectation on the P. Then I want to have my set. That's my indicator. And then times the random derivative. So here, if I'm looking to specify C2, or in this case, it'll be the Z up there, dq/dp, right? So I could write this here as C2, right? So what would that be? Well, the indicator is only going to be 1. This is only going to be 1 on the set HH, right? So this here is going to be equal to the probability under P of heads, heads, times, and then what you're going to get here is your C2 evaluated at HH. So now you're going to get, what is C2? Well, this here, P tilde, right? Heads, heads, we're used to saying that this one here should be P tilde squared. Right, and what is this? Well, I want this to be P squared times C2 of heads, heads, right? So solve here, you're going to get that Z2 at the point HH is going to be P tilde divided by P squared. You can do the same thing, of course, if you want to do, you have to go through all of them. So let's try to do another one. Let's do heads, tails. So you get P tilde for heads, tails. How would you calculate that? Well, it'd be exactly the same. It will be the probability on the P of heads, tails times the random derivative evaluated at HT. Right, we want this thing here. This is going to be P tilde times 1 minus P tilde. We want this to be equal to P times 1 minus P times that Z2 of HT. And so we solve again. We're going to get that Z2 is equal to P tilde over P, 1 minus P tilde over 1 minus P. And so you can see there's a structure that forms like that square you have up here. This counts how many heads. Right? So this here is equal to what we had called P tilde over P times H2. The number of heads evaluated at heads, heads. Right, so that the number of heads coming out when you're on the heads, heads path, this is exactly 2. And you can do the same thing down here. This here will be equal to P tilde over P to the H2 times 1 minus P tilde divided by 1 minus P. So this is at HT. This is T2 over HT. Ideal both be equal to 1. So you're rediscovering now that formula that we had before the break. You're rediscovering this is where that when I said that this is really the binomial example is you take your Zn to this ratio to the number of heads, this ratio to the number of tails. You're rediscovering that formula by going through an example like this one. Did that clarify, Eddie?
Yes, definitely. Thank you.
Other questions about what we did before the break? Okay, if that's not the case, then I'm going to shift gears and we're going to return to change the measure next time. This will be with us for a while. Next time we'll review some of the things we did here today and do some other things too. And so I'm going to start on American options. So just to mix it up a little bit, so we don't just look at this heavy theory all the time. Let's do something about American options. Right. So to read more about American options is both Hall and Shreve 1. They have lots of material on American options. Okay, so the new feature, the ones we had before were called European options, right? So this has nothing to do with geography. It's just two names that are associated with with these two structures. So the ones we had before were called European, and now this one here is called American. There are lots of others. There are Asians, Bermudans, there are Russian. There are lots of different types of options. The main ones are European and American options. So the American options, the new feature, and I cannot spell a feature today. The new feature, this is this early exercise. Early exercise is allowed. Right, so there's more flexibility. There's more flexibility relative to Europeans. Right, so if there's more flexibility, they are going to be more expensive. Right, if you have more freedom with this type of security, then you're going to be paying for it, right? So the price of these options, you're going to be higher, or at least not lower than the European ones. So the new feature is that you can exercise not just at the end, you can exercise whenever you want. Okay, so this new feature here, to keep track of this, to model it, there is a concept called intrinsic value. So the intrinsic value, if we are in section 4.4 in Shreve, this thing is denoted by GN. So GN is FN measurable. If you are in section 4.2, and this is again in Shreve, it's the thinner of the two. If you are in section you're on section 4.2, then what you're looking at here is G of Sn, where G is just a function. So NS is a stock. So we're going to be playing with an example here today. So let's, to get a feel for this, we're going to be looking at examples that fall into the second category. So G of X could be if it's a put, it's K plus X positive part, or it could be the call. So there's just a note here. Often our focus is on puts. So I should say American puts. On American puts, this is often it is, and then this is because the price of European calls the often, not always, but the often equal American. So the word often here, this requires some sort of quantification. So let me just show you where you'll find stuff about this. You can see we are in section 4, right? This is where this is Shreve, the first volume. And we are down. We played around with this before the break, right? And now we're down here in this chapter 4 on American derivatives. So chapter 4 and 5, chapter 4 and chapter 5, be all about American derivatives. You see, there's an American put here. The thing about American call options, this is over here in section 4.5. This is page 111. And the thing that it's being shown here in that, the thing that's being shown here in the case of American call option is that under some conditions, the American option has the same value as the European. So there's no difference in price between American and European call options. And we're going to prove that. This is going to come. We're going to see this. This is going to come later. But it's just to give you guys heads up that the reason that the focus is typically on puts is because of this result that says that calls are often the same. There's no distinction. This early exercise, while it's allowed for call options, it turns out that you don't want to do that. You want to hold on to your American call for as long as possible, and therefore it becomes exactly the same as the European call. That is not true for the put, and so that's why the focus is on often exclusively on the put. So what I want to do here in the last 15 minutes or so is to go through an example just to set the stage for what it is that we are interested in here. And we're going to be looking at the put. Right, so let's do an example. This example here is also in the textbook. So we do an American put. We do an American put with k equal to 5. So this is an example that we have. The setting here is something we have looked at many times. Right? So the starting price of the stock is 4. You can go up to 8, down to 2, go up to 16, go down to 4. And if you go in two tails, you end up in 1. Right? That's something that we have seen. We've seen a lot of times. Right? So for the European one, all the action happens out here in the end. So if I list here the European at time 2, right? So this here is time 1. This is time 0, and this is time 2. If I list the European payoff, the European ones are now red. And what would it be? Well, it's a put. So the European one is 5 minus 16 plus the part. This is 0. Then the next one, this is 5 minus 4 plus the part. This is a 1. And the bottom one, this is 5 minus 1 plus the part. This is a 4. So the payoff, this is the European payoff at time 2. This is something we're familiar with. And the European and the American payoffs at the end are the same. This here is also going to be equal to the American payoff at the end. So there's no difference here out at the end. And remember, when we do dynamical programming, we start out at the end and then we move to the left, right? So we go from here, and then the next thing we want to understand is what happens here. We want to know what happens in this node and in that node. And that's where we're going to see a difference. So say in our familiar setting here, if the interest rate is 25%, then we're going to get P tilde is a half. So let's just stick to the familiar setting. And then how would we go about pricing the European one? Well, this is what you guys are good at this point, right? You take the payoffs and then you move them back one node. So if you look at the European one, I want to know what to put here. I want to know what to put here, right? So we have the payoff at the end is 0 and 1. And so what will be the price here? Well, the price will be you have to take the payoff, discount it. So this is 1 over 1.25. Take the risk neutral expectation, so that's a half. And then you take 0 plus 1. If you work out what this is, that would be something like 2 divided by 5. Yeah. So that was the European one in the top one. We'll also have to do it in the bottom one. In the bottom one, it's 1 and 4. And you do the same calculation, 1 over 2.5, 1 over half, add them up, 1 plus 4. This becomes 2. Right, so this is the European value. This one's at 2, this is at 1. Right, so we're slowly but safely moving from the end towards the beginning. That was the European one, so let's try to do the American one over here. Well, the American one has this early exercise feature. This is given by that function g. So when I look here at this point, so on one hand, I have 2.5. I have 2.5. This is by not exercising, by not stopping. You get 2.5, right? Because that's the value of this payoff you get out here at the end. So, but you can also exercise, or you can stop, or exercise. And if you exercise, then what do you get? Well, then you get G of S1. And what is G of S1? Like this is a 1 here, right? We usually don't stick the stock price at earlier times into the payoff function, but G here is this intrinsic value. So what do we get here if we're in the top one? Well, what is the payoff if I am in the top node? So this is up here, right? So this is G. So this is equal to, so this here was on a heads. So this is G, that would be 5 minus, and then the stock price is 8. So that would be a 0. Okay, so do we want to continue? So not stopping, not exercising, or do we want to stop? Do we want to exercise? Well, if we continue, we have value 2.5, 2 over 5. If we continue, we have 2 over 5. If we stop, we have 0. And this one here wins. This one is the good one. This is bigger. Now let's look at what happens in the bottom part. And this is where it changes. So again, I have this. If I don't stop, so I'm not stopping, then what will the value be? This will give me a 2. And then if I stop, then the value will be what? This will be G of S1, but now I am in the tail state. So it will be 5 minus the value in the tail state, positive part. So what was the value in the tail state? This was 2. This is 5 minus 2, positive part. So now we see you get a 3. So it begs the question, what should I do here? Well, if I don't stop, I continue, that has value 2. If I stop, it has value 3. So that's the difference. So now I'm going to get a 3. Instead of 2, it's worth 3. So this was at time, so again, this was at time This is at time 2. Now this is at time 1. So to price the European, we will just move these two payouts 2 over 5, these two values 2 over 5 and 2, remove them to time 0. But now for the American one, I'll need to figure out what the value is at time 0. And so I'll also have to do, I'll have to do this one. But now I have 2 over 5 and I'll have 3. That's all the way out to time 0. This is at time 1. This is at time 0. So I perform the same calculation. I will have the European one. So I'll have 1 over 1.25. That was the interest rate times the probability. The risk neutral ones, P tilde, that was 1 over 2. This quantity is 1 over 1 plus R. This quantity, this is P tilde. And then what I do is I add them up, 2 over 5 plus 3, figure out what this thing here is, which I didn't figure out. I didn't write down what this here was. I don't know why I didn't figure this out. So compare. Did I write this out? I think what would it be? I think my calculator says 1.36. If somebody could check that, that would be awesome. You compare this with G of S0. Okay, so what is G of S0? What is G of S0? If I call it quits immediately, it will be 5 minus 4 positive part. Because the initial stock price was 4. This here is equal to 1. So you compare the two, the biggest number wins, and the biggest number is going to be 1.36. Right, so that's the value. That's the value of the American. Any questions on this part? This is just how it works in a specific example. We're going to do all the theory that sits behind it.
Yeah, can I ask a quick question?
Yeah.
So, at time 1, if we have S1T, does that mean we always choose to stop since 3 is greater than 2?
Yes, that's correct. That's right.
So then do we never get to like the maximum amount that we can make, which is 4 if we like choose to continue?
I mean, you can't get the max, right? This is not how it works, because you don't, when you're sitting up here, when you're sitting here at this node, you don't know if it's going to go up to 4, or if it's going to go down to 1.
Okay, so we never like take that chance, I guess. We always just stop.
So for pricing American options, it's an interesting question what you're asking here. So maybe you're almost out of time, but let me throw out a game, because this is going to get at what you're asking about. What about this game? So this here is a game of chance. This is a game with rolling a die. All right, so there's 6 sides. 1, 2, 3, 4, 5, 6, and you're equally likely. Here's the game. But here's a rule. So the game is you can roll up to 3 times. And you can stop. You can stop when you want. Right, so when you stop, you get the number of eyes. So 1, 2, 3, 4, 5, 6 in dollars. When do you stop? And what will you pay? Oh, you're always going to get something, right? You're going to get at least $1. And what will you pay to play? So this is going to get a little bit at what you were talking about. Are we just always going to hunt for the maximal payoff, or what? Try to think about it here. Is this game, like you can roll a die up to 3 times, and you can stop when you want. When you stop, you get the number of eyes, like of your last roll. Of your last roll in dollars.
What do you mean by eyes? Number of eyes?
Well, when you roll a die, it's going to show a number of eyes, right? It's going to be 1 eye, 2 eyes, 3 eyes, 4 eyes, 5 eyes, or 6 eyes.
Oh, okay.
Are we good on the game?
Yes.
How much are you willing to pay? When do you stop?
Would it be, because the expectation is 3.5, so would you just, if you're over 3.5, wouldn't you just stop then because you're up?
So here are some suggestions. Stop when you are above 3.5. Is that correct? That's the
Yeah, that's what I'm thinking, because that would be above the expectation. So like,
so that means 4 or 5 or 6. Does it matter? Does it matter that you have 3 rolls? Like, what about if you had 1,000,000 rolls? Sometimes to answer this question here is like an old interview question. This is how, I mean, that's how they come across to me. So the student shows up, one of you guys are going to get an interview question that's sufficiently crazy, and you're going to ask me how to do it, and then it's going to be incorporated into the class next time I teach it. So some years ago, many years ago, a student came back with this one. And so how do you analyze something like this? Well, try to think about the word 3. So what happens if I would put 1,000,000 there instead? Would this thing here change?
I don't think it should, since each roll is independent of the previous one. It's not like you're adding anything from your previous rolls.
So what about if you had an infinite number of rolls? Then when would you stop?
Then you would stop when you get a 6 out, I assume.
Okay, so if you have an infinite number of rolls, you get a 6. But then you can kind of see that the 3.5, this is not going to work for any finite number, right? Because you presumably want to have that your answer converges as the number of rolls available converges to plus infinity, right? Because if you reach 4, 5, and 6, then that will be the same for all no matter how many rolls you can have. And so if you pass the limit, then you would not get 6. So if you have a lot of rolls available, maybe you're willing to waste some of them and gamble a bit more because you have lots of rolls still left to go. Does that make sense?
Yes.
I mean, so at the end of the day, there is no right or wrong answer to this. It depends on the player's preferences. I'm just trying to throw out ideas here. Like, how would you go about analyzing this? And what do we do for the American option? How does it work there? How come that we're not hunting this maximal payoff? Well, in our model, we're not hunting this maximal payoff for very much the same reasons that you're not hunting the maximal payoff here with 3, right? You said 3.5, so you're not saying that you're going to stop when you get 6. You guys immediately said that if you have infinitely many rolls, then you're going to wait until 6. But if you have a lot of rolls, maybe you want to bump this up to say that I'm only going to stop here on the first time if I have a 5 or above. And then when I get closer, maybe I only have a few rolls left, then I'm going to stop when I'm above 3.5. So I'm putting out this question here just for food for thought. And how would you go about analyzing it? How should we get at this? Well, how do we always solve problems? How do we always solve problems? We always solve problems from the right side towards the left side, right? This is dynamical programming. So we're going to use dynamical programming. We're going to use dynamical programming, right? So that means that that we start. So we're going to start at the end and move gradually forward. So we're going to look at the second throw, right? The third throw, we just have to live with the outcome. So we're going to analyze the second throw. We're going to analyze what happens if we add the second throw. Well, what is the expected value of the third throw? So the expected value of the third throw, it's almost impossible to say. Well, that was the one that you already nailed down, right? This is 3.5. So now we could apply the stopping rule. So stop if second throw is bigger than or equal to 4. So this one I believe. But then what about, so now we use the dynamical program, right? At the end, you just have lived with the outcome. So that's the third throw. Now, so we analyze the second to last throw. So that's the second throw. What happens? Well, the expected value of the third throw is 3.5. You stop if the second throw is above. Okay, so that I can understand. But then what about the first throw? So now we're gradually moving to the left, right? What about the first throw? Well, you're going to compare. With next round's value. And what is the next round's value? Well, the next round's value, there will be 6 outcomes, right? And then you're going to get 4, 5, and 6. And then you have to compare with what the other ones. Those have expectations 3.5. So that's 3.5 plus 3.5 plus 3.5 plus 4. It's all equally likely with 1/6. These are the 6 possibilities in the next throw. But because if you roll a small one, then you're going to go out to the third throw, and that expectation has 3.5. If you're rolling a big one, you're going to stop. So the big one is going to be 4, 5, or 6, all happening with the same likelihood. And you compute what this is, and this is 4.25. So now you're going to get this feature that you're going to stop if the first throw is bigger than 5. And so you're seeing you're more averse as the time progresses because you have less and less flexibility. So you're more greedy here than you are there. And that's because here you have more tolerance towards taking a bad hit because you will still have a couple more throws left. So this way of doing it, this here is risk neutral, right? Because you're just comparing expectations. This way of doing it has this feature built in, and this is exactly how we're pricing options. And of course, this is when do you stop? And also, what do you want to pay for this game? Right? So the value of the game. Value of the game, what would it be? Well, you'll have again 6 options. So if I am, what am I? I can roll 1, 2, 3, 4, 5, 6. So the first one will give me 4.25, 4.25, 4.25, 4.25, and then I get to 5, so I have 5 and 6. And this would give me something like 4.67. So this is how many dollars you have to pony up to play the game. If you want to play such a game, then the price is $4.67. This would be one way of trying to answer this question using this theory for American options. Of course, there's no right or wrong answer here. I mean, there's no preferences. I'm not saying that this is the only way to analyze this, but this is one way to do it using this American option theory. Calculating the expected value of continuing versus stopping. And then you move backward recursively, right? So you start out with 3, you could of course have done this with 3, 4, 5, and so on. Right, so this was trying to get at, when do you stop? Well, you don't necessarily hunt the maximal value. There's nothing wrong with hunting the maximal value, but it is not consistent with this way of pricing American options. This is not what we're doing. We went a bit over time today, guys. So are there any questions before we call it quits? Any questions? Otherwise, next time we're going to continue with these 2 strains. We're going to do some more change of measure. And then we're going to dive in. We've done an example now with American options, and we're going to go in and then try to develop some of this theory for optional stopping. Otherwise, there are office hours, and there's also homework up. If I won't see you later this week, I will see you. Next week.
Thank you, Professor.
Take care, guys.